Welcome to Lesson 2A in the Limits and Continuity unit of Calculus. I'm Mr. Stark. In this lesson, the focus is on limits involving infinity, which means we'll talk about horizontal asymptotes and properties of limits as x approaches positive or negative infinity. In Lesson 2B, we'll talk about vertical asymptotes and end behavior models. Let's get started. In order to understand horizontal asymptotes, we're going to look at two functions, 1 over x and arctangent x. The reciprocal function is used in a lot of scientific applications. It's also helpful to understand asymptotes because it has a horizontal asymptote and a vertical asymptote. Let's try to find that horizontal asymptote. Practically speaking, we're looking for a horizontal line that the function approaches. Formally, however, we're using limits to show that a horizontal asymptote exists. So let's get practical. When we look at this graph, we should be able to see that y equals 0 is this horizontal line that the function approaches when x is really big and when x is really small. That's great. And that might have been something that you did in pre-calculus class or previous algebra class. But what we're actually doing is we're letting x approach infinity. So we're taking the limit as x approaches infinity of 1 over x. And we're taking the limit as x approaches negative infinity of 1 over x. In both cases, the result is 0. We found those limits graphically, but we could also find those limits numerically. We could look at a table like we did in a previous lesson, but let's just pretend that we could plug in infinity into the function, which we can't, because infinity is not a real number. But if we could, we would get 1 divided by infinity for the positive side and 1 divided by negative infinity for the negative side. What in the world is 1 divided by infinity? The good thing is we don't need to answer that because we're not finding the function's value at infinity. We're finding the limit as x approaches infinity. So the question now becomes, what does 1 over infinity, 1 divided by infinity, approach? It approaches 0, a finite number. Now I have some questions. What does it mean for a function to have a finite limit as x approaches positive infinity or negative infinity? Think about it. X approaches infinity without bound. A point is moving along the curve forever, forever, forever to the right, or forever, forever to the left. And the result is just a number, a real number. Y equals this number is the equation of the horizontal asymptote. Let's formalize that with proper notation. If the limit as x approaches negative infinity of f of x equals L, and L is real, then y equals L is a horizontal asymptote of f of x. Similarly, if the limit as x approaches positive infinity of f of x equals m, and m is real, then y equals m is a horizontal asymptote of f of x. Once again, notice that x is increasing or decreasing without bound, while y is approaching one number. Here's a very direct example of finding horizontal asymptotes of the function arctangent x. The equation is written as f of x equals a tan parentheses x, but you might recall that it could be written as tangent inverse x with a -1 superscript. Let's apply what we learned in the last example to this one, which means we're not just looking at the graph and trying to identify the horizontal line that the function approaches. We are officially, formally, taking the limit as x approaches negative infinity of the function and the limit as x approaches positive infinity of the function. By the way, my limit notation is horrible. I didn't include the argument, which is writing f of x or arctangent x to the right of the limit. Anyways, as x approaches negative infinity, as x gets smaller and smaller and smaller along the arctangent curve, the y value is approaching -pi/2. We know that not just because The increments for y on this graph are pi over 2, so positive pi over 2 and negative pi over 2. But more specifically, because arctangent is dependent on the original tangent function. And that tangent function has vertical asymptotes at positive pi over 2 and negative pi over 2 and 3 pi over 2 and 5 pi over 2 and so on and so forth. It follows then that as x approaches positive infinity on this function, on the arctangent function, the y value is approaching pi over 2. In both cases, the results of the limits were finite, negative pi over 2 and pi over 2. Therefore, the horizontal asymptotes are y equals negative pi over 2 and y equals positive pi over 2. Hey, this function had 2 horizontal asymptotes. Amazing. Let's end this lesson with the properties of limits as x approaches positive or negative infinity. These properties are very similar to the properties I shared in lesson 1a. I mentioned that those properties are consistent with the properties of real numbers. I also mentioned that those properties could be found online or in a calculus textbook. I included some page numbers for the Finney textbook, but if you have a different edition, you might need to flip a few pages forward or backwards. To conclude that the following 6 rules work, these conditions must be true. L, M, and K are real numbers, so they can't be infinity or negative infinity. The limit as x approaches positive or negative infinity of f of x is L. So as x increases or decreases without bound, the limit is finite. And the limit as x approaches positive or negative infinity of g of x is M. If these conditions are not true, it's still possible that these rules will work. It's just that they're not guaranteed. I hope that makes sense. The sum rule states that if you take the limit of a sum, the result is the sum of the limits, L and M. The difference rule says that if you take the limit of a difference, that's equal to the difference of the limits, L minus M. If you're writing all these down, by the way, you could use those double quotation marks to show that you're duplicating the same expression. The product rule, as expected, states that if you take the limit of a product, then the result is the product of those limits, L times M. The quotient rule states that if you take the limit of a quotient, then the result is the quotient of the limits, except that the limit in the denominator must not be equal to 0. Otherwise, we have a divided by 0 issue. We don't want that. We have 2 more. The 5th one is the constant multiple rule. It states that if you take the limit of a constant times a function, then the result is that constant times the limit of the function, k times L. And finally, the power rule. It states that if you take the limit of a function raised to a rational exponent, then the result is the limit of that function raised to that exponent. Remember, a rational number is simply a number that could be written as a ratio, like 2/3. These 6 rules are properties for limits. They're different than the algebraic limiting techniques. There were 5 that I presented in lesson 1b. And that reminds me of the approaches that we take for calculating limits: numerical, graphical, algebraic. So try to keep those separate but connected in your brain. Finally, I want to mention that these same rules are going to show up again, but in the context of derivatives, the next unit in calculus. So they'll have the same names, but they'll be the rules for derivatives, like the sum rule for derivatives, the difference rule for derivatives, and so on.